All right, this is the final section of 6.3, vectors in a plane. Today I need you guys to be awesome, all right? Pay attention, stay focused. You will use vectors to model and solve real-life problems. Here we go. Decomposing a vector. A vector can be represented by the product of its magnitude and its unit vector. Okay, so here's a unit vector. This comes from the unit circle, actually. This is the x component here, the horizontal component, the cosine part. And the sine part is the vertical component, or the vertical y component. And 10 is just how long that is. This is the magnitude. So this is a unit of 1, and this is my magnitude. So we're talking about this vector here. We would have angle here, and the magnitude is going to be how long that vector is. In this case, it would be 10. And theta is 20. So we use the SOHCAHTOA for this right triangle. We can say the adjacent over the magnitude, or magnitude of 1 on my unit circle. We'll get the cosine of theta times whatever this is here. The magnitude will give me the horizontal component. Using the same logic, we can use the sine of theta times the magnitude will give me the vertical component. These two are the two pieces that we can break this vector down into. The part that goes to the right and the part that goes up, or something I plus something j. Okay, that's where that comes from. Don't try to put this in your calculator the way you see it here, because the I means the horizontal part, and the calculator does not know how to add the horizontal component with the vertical component. So here's my magnitude, that's the 10, and that's just the unit vector. Okay. All right, distributing the 10, we get 10 times cosine of 20, which is the horizontal piece here, that's the I part, and 10 times the sine of 20, which that's the vertical part. And I like to write this as a shortcut because these two numbers will always be the same. The angle is going to be theta, it's going to be always the same in here. So it's just 10 cis theta, or magnitude cis theta, and the cis stands for cosine and sine. All right, let's try one. A ball is thrown in the air at an angle of elevation of 58 degrees at a constant velocity of 25 meters per second. Compute the horizontal and the vertical components of the resultant vector. Okay, so this is my resultant vector, and I want the part that goes this way and the part that goes this way. My vector u, so I'm going to say 25 cis 58. So my horizontal component is just the cosine of 58 degrees times 25. And my vertical component is just sine of 58 degrees times 25. Okay, so if you put that in your calculator, you should get 13.2 going this way and 21.2 going this way. And if you square these and add them together and take the square root, you should be able to get back to the 25. All right. Now let's look at this one here. Adding two vectors. The last problem only had one. Now I'm going to add two of them together. So here's vector u. The magnitude of this is magnitude of v. And then this is vector u and has a magnitude of u. Okay. So these are my two parts of it. This is the horizontal part and the vertical part. And for u, this is my horizontal part and my vertical part. And notice that this is angle theta. And then since this is not angle theta, I'm going to call that angle alpha. Okay. And so this will be the magnitude of v times the cosine and the magnitude of v times the sine. For this one over here, vector u, we have the magnitude of u times the cosine of alpha. You notice that both of these are measured from the 0 on my unit circle. That's the only way your calculator knows how to do this. Okay, so if they're given this angle in here, you can't use that. You have to subtract that from 180 and you get this angle over here. So, and then we have the vertical component would be the sine of alpha times the magnitude. So if we want to add these together, we add all the horizontal pieces together. We add all the vertical pieces together. So we're going to add magnitude of v times the cosine of theta plus the magnitude of u times the cosine of alpha. Notice you're adding the two cosines together, or the two I parts, the two horizontal parts together, and you're adding the two sine parts together, the two vertical parts. So these are the vertical parts are sines. You add those two together, and add the two horizontal parts together. Okay. Sometimes they will help each other. Sometimes they'll work against each other. Right? If this was a tug of war of some kind or a piece of rope, and there's something tied here, and you're pulling this way, and your friend's pulling this way, you'd be working together, moving the weight in this direction, but you'll be working against each other, going on the horizontal direction. So that's what it means. So in order to find u plus v, you're actually finding this one over here, which you remember if you put head to tail, you make a parallelogram, and that's the resultant vector is the one that's right in the middle there. Okay. Here, let's try one together. Vector u has a magnitude of 10 at a 20-degree angle, and vector v has a magnitude of 16 at a 75-degree angle. Draw the resultant of the vectors, and then find the magnitude and direction of the resultant. So try and go ahead and draw this. Remember that you're going to have to use the angles from 0 on the unit circle, okay? Because it doesn't give you anything. This is not bearing or heading or anything like that. Okay, did you get the picture drawn? Well, this is the way I have it drawn. 20 degrees from the 0, that's vector u, and it has a magnitude of 10. And vector v is 75 degrees, has a magnitude of 16. Okay. Now what does the resultant vector look like? Well, if we make a parallelogram like that, or put this one on the end of that one, we will have that resultant vector. That's a resultant vector. All right, removing those dotted lines here. So both of them are going to be pulled to the right. Both of them are going to be pulled up. So that's why when we add them together, this is going to be much longer than both of them going to the right and longer than them going up. This one's working, u's working more to the right than it is up, so it only adds this much to this here, but it's pulling more this way. And this v is actually pulling more up than it is to the right. But that's you'll figure that out later. Okay, so for vector u, we have 10 cis 20. For vector v, you have 16 cis 75. Now we're just going to add the two cosines together and add the two sines together after we distribute the 10 and the 16. So u is 10 cis 20, v is 16 cis 75. So adding the two cosines together, the two I components together, adding the two j components together, we get 10 times cosine of 20 plus 16 times the cosine of 75. You can finish that on your calculator and also do those on your calculator. 10 sine and 16 sine 75. Okay. So your final answer here is 13.5i plus 18.9j. Okay, now we found the component form, but what did it ask me for? It asked me for the magnitude. So I have to come back and find the magnitude and the direction. Well, I haven't done that yet. Okay, we did that yesterday. So we find the magnitude, we square these, add them together, take the square root, right? So that will be 23.2. Square these, add them together, and take the square root. Okay, you can check that out on your calculator. Then to find the angle, remember that tangent of the reference angle is sine over cosine, and taking the arctangent of 18.9 over 13.5, I get 54 degrees, 54.5 degrees. Okay, and we're in quadrant 1, so my reference angle is actually my angle. So that's all the answers there. Okay, so there's my magnitude, done, the direction, done. Okay, so let's recap here. The 13.5 is the horizontal component of my resultant vector. The 18.9 is the vertical component of my resultant vector. The magnitude is 23.2. Okay, that's what that represents here. And then the 54.5 is the angle that makes from 0. All right, here's some rules if you are getting lost with so many different steps. Finding the resultant vector, first write it as a cis problem, cosine I and sine j. You're going to add all the i's together, add all the j's together of your two vectors. Then find the magnitude using like the Pythagorean theorem, a squared plus b squared, take the square root. Find the angle, use the tangent. That finds your reference angle, not your real angle. Okay? I'm going to try and do this one together. These two forces are holding up this weight. Okay? So we have a 100-pound force at an angle of 15 degrees and a 70-pound force at 43 degrees. Find the direction and the magnitude of the resultant. So let's see. Try and stay ahead of the game here. We've actually done enough problems together in class and in the homework that you should be able to get through some of this on your own. So I'm going to first draw my resultant force in. So my resultant force is going to look like that. Okay, now I'm going to set up my problem. I'm going to call this one U and this one V. So U is going to be 70 cis, what do you think? Cis 47. Because remember, it's always from the 0. Okay, so this angle in here is 47 because this goes all the way up to the vertical. That's for 43, so the rest of this here has to be 47. And this 15 degrees angle from the vertical has to be 105 because this is 90 plus the 15. Remember, when you use sine and cosine on your calculator, the only way it knows how to do it is from the 0 on the unit circle. Alright, so now we have 70 cis 47, 100 cis 105. Now we're going to go ahead and add my two horizontal components and two vertical components together. So let me rewrite that. So there'll be 70 cosine of 47 degrees. Notice I'm adding the two cosines together. 100 times the cosine of 105. Okay, and just realize when you do the cosine of 105, you're going to get a negative number. So because this is going to work against this, because it's pulling in the opposite direction as the u vector. And these two are working together, so both of these should be positive. So 70 sine and 100 sine. So you add the two sines together and add the two cosines together. Okay, finishing that off on your calculator, I get all of this equals 21.9. And adding all this together, I get 147.8. You notice that both of these numbers are positive. We're in quadrant 1. Sometimes if you don't draw this exactly right, it might look like it's in quadrant 2, but always check here at the signs of these numbers. Then when I take the magnitude, square these numbers, add them together and take the square root, I get magnitude of 149.4. That's the length of this resultant vector, this red one here. It should make sense to you that if you're pulling 100 this way and 70 this way, it has to be more than 100 going this way, right? Very good. Now you're going to find the angle of the force, sine over cosine. That is going to give me arc tangent of 147 over 21.9 gives me 81.6 degrees. We're in quadrant 1. We're good. Okay, so we're done with that one. One more. A plane flies at 500 miles per hour without wind with a bearing of 330 degrees. During its flight, the plane encounters a 70 mile per hour wind in the direction of north 45 degrees east. What are the resultant speed and direction? So we're kind of doing the same things, but make sure you draw the picture correctly. I'm going to let you do this. This is last example before you have to do one on your own on the Google form. So try to do your best without looking at me, watching me do this. Okay. All right. So starting like that, I get a heading or bearing of 330 degrees. Remember, this is 330 going this way from the north, going clockwise. And the only way I can do this with my calculator is that I go from 0 on the unit circle. So this is really 120. Oh my gosh, Mr. Ho, how did you get 120? Well, let's see. If this is 330 going this way, that means there's 30 left in this little piece in here. And this is a 90-degree angle plus that 30. Okay, so it's 90 plus 30. That's how I got the 120. All right. So we have 120 angle, and then we have a wind that's facing north but turns 45 degrees to the east. So it goes that way. Okay, this is just a little note for this angle right here, 120. Remember that bearing is clockwise from the north, and then your angle has to be from the 0. Okay, so the angle from 0 here would be that right there, and this is my resultant vector, right? Put head to tail, make that parallelogram, and the resultant vector is the one that goes through the diagonal. So we got this thing all set up? I think so. If you think you can finish this from here, then go ahead and do it. Otherwise, we can watch some more. So we have a 500 cis 120. That gives me the flight of the plane. And we're going to add this piece here, right? We have to add this vector over here, the wind. So the wind is actually 70 miles per hour, and cis 45, right? That's for 45 angle from the 0. Okay, 45 opening up this way from the 0, just like 45 going this way. The wind's blowing that way at 45 degrees. All right. Now we add all the cosines together, add all the sines together. So we have 500 cosine 120 plus 70 cosine 45, I plus 500 sine 120 plus 70 sine 45j. Finishing that on my calculator, I get this. And then I want the resultant speed. This is all speed, right? Miles per hour. So this must be miles per hour. Resultant speed, that means the magnitude. Magnitude, I get 522.5 miles per hour. The wind is actually blowing up and to the right. So it's going to help the speed a little bit. Like this right here, part of the 70 miles per hour is going to be added as a vertical movement. And then the tangent would be 482 over 200, and the negative goes away because that's the absolute value. Reference angles are never negative. And I get 67 degrees, 0.4. And you notice that this is a negative and a positive, and negative and a positive means we're in quadrant 2. In quadrant 2, what I have to do with this? Subtract that from 180. I get 112.6. So that means this angle here to the red vector, here the resultant vector is 112.6. And the magnitude is 22.5. And if that's the case, how do I find the bearing? Well, same way as I did over here. I'll let you actually figure that out. I know you're smart enough to figure that out. The bearing, since this problem was given in bearing, so you have to also find the bearings, right? Since the airplane flies with a bearing of 330 degrees, it wants, and then it says what direction? Well, you have to give it back in bearing form. So this is 112.6. So going by this logic over here, you figure out the difference. Subtract that from 90, right? And subtract the difference from 360. You should get this. Okay? Right here. All right. Making the diagram. Here's some notes on making the diagram. If you have no point of reference, if they just give you a number, then it's always, you always draw the vector, draw one of the vectors on the positive x-axis. Just point it to the right. Okay? Put the starting point at the origin and point it to the right. If they don't give you anything, just leave it as a 0, vertical, and all of it horizontal. This makes your problem a lot easier. We can throw one of the numbers away. Okay, so if this is a magnitude of 7 and they don't give you an angle, then put all of that 7 on the positive x-axis going to the right, and you don't have to worry about the vertical. Bearing. Bearing is always clockwise from the north. North 20 degrees west means to turn 20 degrees towards the west from the north. Start at the north and then turn 20 degrees to the west. Once it's given an angle, start at 0 on the unit circle. Okay, if it doesn't say bearing, it just says 20 degrees, then start from the 0 and go up 20 degrees from the unit circle. And then make the diagram as proportional as possible. If one is 500, the next one's 2,000, then make sure that one's like 4 times as long. Otherwise, your drawing's going to be all weird out and you can't figure anything out from it. All right, so that's it. Do the Google form and do a good job.